like. These code sequences would lead to like a few entries in this vector dominating all others, and you're just recognizing, okay, this has been compiled and that has been compiled. So what they do is they filter out those sequences that occur a lot, in the sense of they divide that value in that vector by the number of executables that exhibit this feature. So in a way, things that occur very often will get normalized. And then you just calculate the cosine and see whether it's similar. Advantages, it's simple, it's fast, and it's not totally localized, so it does take the entire binary into account. The papers that they've published furthermore claims that it's resilient against code reordering and resilient against code motion, which I kind of dispute. The thing is that resilience against code motion breaks when you do this over longer sequences, because, well, you're looking at unordered sequences of instructions, and the compiler will reorder within that sequence of instructions within a basic block. But the compiler will also reorder basic blocks. So when you choose your n to be fairly large, and the compiler starts swapping basic blocks around, your resilience against code motion breaks. And surprisingly, or the average basic blocks are surprisingly short. Like the average basic block in our databases is between 4 and 7 instructions. So really you are breaking as soon as you start being a little bit more expressive. Yeah, so this is kind of limited. It's also extremely non-resilient against different choices of mnemonics by the compiler. So if the compiler decides to replace, I don't know, a move with something else, then, well, clearly that will distort the results. And we're not even speaking about an attacker trying to be malicious yet. If I was malicious, and I wanted to break nperm's classification in my build process without actually having to do anything, I would insert something into my executable, which is an if condition that is always going to be false. And after this if condition, I'd call some function. And this function would never actually be called during the runtime of the executable. And I'd create an assembly file in which I put 10,000 times the same instruction. And then I compile and link the entire thing and release the bug, or release the virus. So what happens to this algorithm then? Well, we have 10,000 times the same instruction in a row. And we're counting all unordered sequences of instructions of a certain length. So I'd say we have 10,000 times knob. And then we count, okay, we have one occurrence of the sequence 5 knobs in a row at the first instruction. Hey, we have another occurrence of this at the second instruction, and so forth. So this instruction sequence that you've chosen for this piece of assembly code will just have a ludicrously high count because you're counting at every possible offset, right? So you'll have a value of 10,000 essentially, or 9,900 something in the vector for the 5, or in that entry for the 5 knobs. And this is an instruction, or an instruction sequence that doesn't occur naturally. So it will not be normalized away. So that means that when you actually try to do the comparison thereafter, the stuff up here doesn't change at all, but one of the two down here is made very, very large, which means you decrease the similarity more and more. So in essence, you can build an automated build process which will emit to completely identical executables that are not similar at all by this measure if you just change the knob to an add. All right, so that stuff is kind of brittle. The next approach is something called basic block distance, and is done by people at Microsoft. What they do is they build a sort of hash function. So you have a hash function that takes a basic block, normalizes away the addresses, and then hashes it some way onto the numbers of 1 to m. And then you have a vector of m bits, and you go over an executable, and whenever a particular basic block, like you take every basic block and you hash it, and you set the entries in that vector to 1 if that basic block occurs, and leave it 0 if it doesn't. So you get a bit vector that represents the basic blocks in that executable. And the big advantage of this is it seems to scale surprisingly well. Like they're doing, like, using this on really large quantities of executables. Trouble is though that building a decent hash function here is not easy. And secondly, especially building one that is resilient to compiler changes and to compiler optimization changes is really difficult. So, yeah, unlike unless you manage to build a hash function that can deal with people reordering instructions and doing stuff, it's not going to be resilient to what's compiler changes. But from what I've seen of all the three approaches, I think this one is the one that at least carries the most promise. So clearly, after bashing the competition, I'll go over to speaking about what we're doing. We do structural classification. The idea behind this is you take a program and you interpret it as a directed graph, and then you do the comparison based on that graph. And in essence, we want to build, or we're building something, well, we have built. I get confused with the time sometimes. So we built a system where you submit executables, and we try to automatically unpack them, remove the runtime encryption, disassemble the executable, generate flow graphs and call graphs from the executable, and then run a comparison algorithm that compares the structure of the executable with the structure of the other executables that we've classified beforehand. And those of you that have been doing patch analysis in recent years might know why and how we're doing this. And, well, I'll begin to speak a little bit about the automated unpacking. The thing with automated unpacking is that in the worst case, unpacking can be made arbitrarily difficult by the attackers, but it does require some investment by them. And the usual approaches to unpacking are something like manual debugging and dumping of memory, which is terribly time-consuming, and people will start playing silly tricks with your debugger. Most AV engines actually emulate an x86 CPU and a few of Microsoft's API calls, so that they can step through the packer and then be fine. The downside of this is that packers and malware authors have gone towards calling weirder and weirder Windows APIs and depending more and more on undocumented return values from these APIs. And clearly your AV engine is not emulating the undocumented return values correctly and then not properly decoding this. This was what Storm did and why a lot of the AV emulators failed on Storm. And then there's the other approach, which is writing packer-specific code for every packer. Problem is you need a building full of reverse engineers to do that, and some people might be able to afford it. We can't. Our solution to this was we'd like to have debugging, but in God mode, like no anti-debugging, please. So what did we do? We took a full x86 emulator and we modified it so we had Python bindings and callbacks on every instruction fetch. And then we installed Windows in that emulator, which is a bit painful because installing Windows XP into a slowly emulated environment does take some time. The advantage is that you don't need to care about emulating APIs because you are running Windows. You're running Windows slowly, but you are running Windows. And there is no debugging, hence there is no anti-debugging. And somebody will then think about some anti-emulation tricks at some point, at which point we will be able to deal with that by just running the trace in the emulator once and running the same trace in a hardware ICE and then seeing where the two instruction flows deviate, and then you see where they're playing tricks with your emulator. You fix your emulator and their trick is gone. So I'm quite confident that that'll work fine. And we have another advantage. We really do not need a full reconstruction of the binary for unpacking. We just need a significant quantity of memory, well, a somewhat significant quantity of memory, where we can extract decent disassembly from. And what we do for unpacking is we really just take the executable, we emulate it for a few million steps, and then we take repeated snapshots of memory, and whenever the memory starts looking nice, we start disassembling it, and then we take the nicest snapshot that we made and work with that. So I have a bunch of slides on how the actual comparison algorithm works, but I've given many talks over the years over this algorithm or about this algorithm. Should I speak about this or should I skip the next 15 slides and go to the other stuff? Who here would like to hear about the comparison algorithm? Raise your hand. All right. Okay. So yeah, the idea is you take the executable and you disassemble it, and the executable itself is a graph of graphs then. What do I mean with a graph of graphs? You have a call graph, which means you have the graph that consists of all the functions and how they call each other. And every function itself is a flow graph, because you have the basic blocks and how they relate to each other. So now you have a big graph, and every node in that big graph is a small graph. And now the idea is that you want to compare the program based on this structure. So we have a call graph here of some piece of malware, I think it's MyDoom. And we have some flow graph here, just as a visual illustration of what I'm talking about. And The thing that's cool about these graphs is that the program logic is encoded to a certain extent into these graphs. So if you change a call from string copy to strn copy, you change the call graph, and if you add an if into some function, you change the flow graph of that function. So in a way, the graphs are the shadow of the program's semantics. So you have the program up here, and clearly we can't analyze the semantics properly, but the compiler will encode these semantics into these graphs, and we get these graphs, and that is at least something that we can work with. The nice thing also is that most compiler optimizations leave the core graph invariant, meaning almost all compiler optimizations up until 2 years ago or so would not change the core graph. They would work on the function level only. And even now, with something called whole program optimization, the core graph stays largely the same. Not completely the same, but largely the same. So a comparison of programs through the structure of the graphs should be resilient to compiler changes, but at the same time cover the entire executable and be able to, well, see these parts of the executable we've seen over here. Okay, well, the advantage of this is it's neither localized nor brittle. The disadvantage is you need disassembly. And in the world of malware, where people are thinking that they have 60,000 new samples a day, disassembly is comparatively expensive as an operation. So whatever we're doing here, it's not something that you'll be running on your own laptop just because you need to have an emulator for unpacking. That takes some time, and then you need to disassemble, and then you need to run a large number of heavy computations on a bunch of graphs. Now, a different question is, how can we compare two graphs efficiently? And the mathematician will tell you that comparing two undirected general graphs is NP hard, so that's going to be expensive. We are in the lucky situation, though, that we don't have general undirected graphs. We have very specialized, highly structured, directed graphs with a lot of extra information. The trouble, though, is we don't want to have a yes-no answer. Yes, these graphs are the same. No, these graphs are not the same. We want to have some sort of approximation. We want to have something, hey, we know these graphs are not completely the same. Please build me the best mapping between these two graphs that respects the structure of the graph. So in essence, you want to build, in math speak, like a graph homomorphism that covers most of the graph. Right? So what do we mean with something that respects the structure? Well, it shouldn't matter whether you first have a node k and then look at, well, map it over to the other executable, to the other node to which it belongs, and then consider its children, or whether you first take k, go to its children, and then map them over to the other side. So in essence, it shouldn't matter whether you go here or here. In essence, you want to have a sort of commutative, well, yeah, whatever. So how can we build such a mapping? The way that we build this mapping is that you take a function and you assign a 3-tuple of numbers to that function. You can take an arbitrary graph invariant, but in the old days we used the 3-tuple of numbers. And that 3-tuple was the number of basic blocks in that function, the number of edges in the flow graph of the function, and the number of sub-function calls. And what you do then is you have these two big bags of, well, nodes with 3 numbers on them, or 3 big bags of 3 tuples of numbers, and you associate those with each other that are unique on both sides. So if I have a node here, and this value occurs once and only once on the left side, and once and only once on the right side, I say these two functions are going to be the same. Yeah, and through this step, you can associate a few functions, not many, because the graph invariant that we've taken is very lossy. There's many graphs which have the same invariant here. So after you've created a bunch of them on a global level, you try to make use of the graph structure, because as of now, we've really just looked at the nodes as a set, right? So you now try to make use of the graph structure and look at the neighborhood of those nodes that you've associated. So, for example, in this picture here, the blue nodes we have no idea about. The red nodes we have successfully associated because this signature here is unique on the left side and on the right side. So we know this belongs to this. This is the same as this. And now we consider only the neighborhood of this node, and the neighborhood consists only of these two nodes. And out of a sudden, this signature up here, which was not unique and occurred multiple times in the entire graph, only occurs once in the immediate neighborhood of a node. So what you do is you create a few points that you know are the same, and then you improve from them. Like you incrementally build a better and better mapping from them. So because these signatures are now unique, you associate the nodes,